Next question, how can we model trends? Right, so I mean, we are now looking at like how to address different forms of non-stationarity. Well, we've seen the differencing can be done, but has some problems. If you have a trend, one thing you could do is you could detrend and get rid of the trend and make it in this way stationary. So the problem that we have with detrending is that it is not well specified what a trend actually is, right? There is no mathematical definition for what a trend is. A trend is essentially just a smoothed version of the series. And the problem now is, well, we still need to forecast that trend, right? So, and now, of course, if you do something like what ETS does, where you say I have a linear trend or I have a multiplicative trend, well, if you say my trend is linear, then the forecast of that trend is trivial. It's this, right? But if you just do like a, for example, STL decomposition, what we are seeing down here, where your trend is basically just a smoothed version of your series, well, what's going to be next? Is this happening? Is this happening? We don't know, right? So you still need to forecast it. You don't really gain anything. Okay. Yeah, I mean, one thing, well, I've already told you that to get rid of exponential trends, you do a logarithm. It turns out a logarithm, well, it's a very strong transform. Yeah, so logarithm or Box-Cox transform, right? So it makes exponential trends linear. That's great. It also stabilizes the variance. But the thing is that the logarithm, yeah, is a very strong transform. What does that mean? So the thing is that if you, so let's say, you know, you have a series with very different values. Now you do a log transform, everything gets squashed together a lot. So now you have very small errors in your log space. Now you do the exponential and they blow up, right? So it can be quite dangerous, right? Because your fitting algorithm thought, oh, that's a small error, it's okay to do that. And then you do the exponential and now suddenly you have a huge error, right? So logarithm is a strong transform and we need to be a bit careful with strong transforms. And that's why Box and Cox came up with this Box-Cox transformation, where the idea is, well, I have this parameter lambda, where I can tune kind of the strengths of the transform. So if lambda is 0, I have the logarithm, and if lambda is non-zero, I do this power transform, and for example, if lambda is 1, I do essentially nothing, right? If lambda is 1 here, I just subtract 1, so I don't do any power transform. I leave the data as it is, just shift it a bit. So in that sense, the nice thing of the Box-Cox transform is that you can now really tune the strengths of your logarithm, so to speak. But the problem is that now you have this parameter lambda that you need to tune, and it turns out it's actually not so easy to tune this parameter lambda. So yeah. Another idea that is nowadays really quite standard in machine learning is this idea of window-wise normalization that I first came across in that work of Smul and Kuber in 2016. And then we adopted that in 2017 in our work, where the idea is, okay, well, we have an input window, we have an output window. Let's just normalize only the windows, right? We are not going to normalize the whole series before we do something with it, but we normalize each window. And now you can do different things. You can calculate just the mean over your window. Smul and Kuber in 2016, if I remember correctly, they used something like the level or the trend component of a transform from the last value in that window or something like that. But yeah, the idea is you take the mean over the window and divide by that, for example, or subtract that, or you can also divide by it. Yeah, and it turns out window-wise normalization has a couple of advantages, right? So it is a bit similar to batch normalization, right? So in machine learning, very big batch normalization. It is kind of very similar idea. And what you do now is that instead of saturating on the absolute values of the training data, it is now saturating on the absolute value of the steepness of the trend in the training data. So basically, if your training data looks like this, the trend that you are going to forecast is never going to be steeper than this last trend that you have seen here. And well, on the one hand, sure, it's a bit limiting because you cannot forecast exponential trends. Like they cannot, continue growing. But if you think about it, that is probably even a good idea for a forecast, to be conservative, right? So forecasting exponential trends confidently into the future many steps out, that's always dangerous, right? So and if you do that, I mean, you are still able to predict really very steep trends, right? This is an example from one of our papers. So your training data is only the black data, and now you see you have here in blue, that's the test data, and we have our forecasts in green here. So you see, like, you can easily pick up that very steep trend just by doing window-wise normalization. Yeah, here's some example R code to do it. And you see this is that air passenger series where I did some window-wise normalization, and you see it really kind of gets rid of that multiplicative trend. And really makes the series quite nice, and just having a seasonality that you can easily model with a machine learning model. So this window-wise normalization has been around for quite some time and has been used quite effectively in machine learning. It has since been reinvented for deep learning under the name REVIN, Reversible Instance Normalization. To be fair, REVIN is a bit different. It has a couple of trainable parameters. But the original paper didn't have any ablation study as to if these trainable parameters are actually really doing something useful, or if the main advantage from the method is really just the window-wise normalization. So I mean, a lot of papers now, they say they do REVIN. I think they could probably just do window-wise normalization and it would do the same thing for them. But if you read REVIN, then that means window-wise normalization. Yeah, another thing about trends, there's quite some expert knowledge that you should use about the trends. I mean, I've said it before, always be careful with strong trends. Exponential trends eventually will slow. As an example, I mean, how much more, can Facebook grow until every person on Earth has 5 accounts each, right? So yes, maybe Facebook, Amazon AWS, Uber, like, these startup companies, they have had exponential growth, and sometimes over decades, right? So Facebook had exponential growth, probably 2 decades, AWS as well. So it's difficult, right? So sometimes you do need to forecast that exponential trend, but eventually it will slow, just because you run out of people to sell your stuff to, or you run out of, I don't know. I mean, like the Earth is a limited place, right? So if you sell iPhones, I mean, at some point you run out of people selling whom you sell them to, and you run out of material to make the iPhones from. And it turns out that even a linear trend can be sometimes, or is very often, a bold assumption if you extrapolate it far enough into the future, right? So even linear trends usually slow at some point. And that's the whole idea of a damped trend, right? So things like damped trend, exponential smoothing model, that's not justified from the data. You don't see in your data a damped trend. The idea is just, let's be conservative about our forecasting. Let's dampen the trend. Forecasts it's always a good idea to make forecasts that are conservative. Leads to better accuracy usually, and to not looking stupid by confidently predicting things that don't happen.